Hi everybody, this is Bruce again here. It's been a while since I've posted anything on this channel related to engineering computer science projects. Today I'm going to be talking a little bit about a program that I wrote called Maze Runner, written in Common Lisp. Now, this program can also be written in pretty much any language. It's a very simple program actually, even though it looks like it's executing a more sophisticated algorithm. So let's just run it here and see what it looks like. Okay, so here we see the little bug enters here at the top left-hand corner, try to find its way all the way down to the bottom right-hand corner. Now, as you watch the little bug running around in the maze here, you might think that there's a backtracking algorithm that's in play here, but in fact there isn't. You see here that it finds its way into a dead end and then it finds its way back out. So this looks like it's backtracking back out, but as I will explain in a minute, it's really quite a bit simpler than that. This is a very simple algorithm, and it just goes to show that if you pick the right algorithm, sometimes you can execute a program. It's going to come up here, back its way back out, and then it will be finished. So you can find sometimes a very simple solution to what appears to be a complex problem. If you'd like to experiment with Common Lisp and you don't have an environment set up already, it's very easy to install a integrated development environment. One I would recommend is called Portacle. That's Portacle, which stands for Portable Common Lisp, IDE, which is Integrated Development Environment. So just search for that. You will come up with a list here. And this one is the one you want, Portacle. It's portacle.github.io. So when you select on that, you have an opportunity to download for Windows, for Apple, or for Linux. Now the nice thing about this is there's no strings attached. There's no subscription services or anything that you have to join or register yourself online or anything like that. Another nice thing about this is that it's quite small. You can even put it on a thumb drive and stick it in your pocket and take it to another computer and have your entire development environment there ready to go when you are. Alright, I'm going to give you a brief introduction to familiarize you with the Portacle and Emacs environment in case you haven't worked with it before. Just enough to get you going. Let's say you want to start a new project. When you open up Portacle, you're going to get this Emacs editor function, which gives you multiple buffers. You have a buffer here, which is your scratch buffer, and you have a buffer down here, which is what's called a REPL buffer. REPL stands for Read, Evaluate, Print Loop. So this is where your user cursor is. Now, if you want to start a new project, what you'll want to do is to highlight everything here and hit delete. Enter at least one character, otherwise it won't have anything to save. Once you've entered something into this scratch buffer, you can come up and do a save as. Down here at the bottom is where you're going to get your prompt. So you can name the file whatever you want. Let's just say X project. Now the important thing is to remember to put the extension of LISP on it. Once you have put that on there, it's going to ask you to confirm. You confirm with another enter or a carriage return, and now you have created a new project. The next time you want to work with this project, you will use your open file application. So I'm going to show you that in just a minute. So that's the case if we're starting a new project, but most of the time we're going to be working on an existing project. So what we'll want to do is come up here to our scratch buffer where we're going to load in our source code. Under the File menu, Open File, we will find in our root directory, I have a separate projects folder. So I'm going to open that up. And then we're going to look for the file, which in this case is called Maze Runner 20. Under Maze Runner 20, we have two entries. One of them is an FASL. This is an assembly language file. That's not what we want. We want the text file, which is noted as a file association file, and it is got a magnifying glass next to it. So I can either double click on it or click on it and say open, and it will load it into what used to be our scratch buffer. Now the next thing we want to do is we want to compile all this code. In order to do that, we hit Control C, Control K, and it will compile the entire buffer full of code, everything. Now you can also, when you're working on things, you can compile a single function by simply selecting anywhere in the function and typing Control C, Control C, and it will compile only that function, or even definitions. You can even defining a variable, you can compile that. It all needs to be compiled. Next thing we need to do is we need to get rid of one of the features that's in Emacs that it defaults to, and that is the parenthesis editing feature. So down here by the user prompt, if I type a left parenthesis, it will enter a right parenthesis as well. Now this actually gets in our way and becomes somewhat of a nuisance when we're trying to edit, so we need to get rid of that. The way we do it is we select whatever buffer we want this to be active in, and we type meta x. Meta on the PC is alternate, and meta on the Apple is an opt, I believe. So we type Alt X on the PC, and then we type in what's written right here. It says pair edit dash mode. So you don't even have to remember anything. Just type Alt X and then pair edit dash mode, just the way it's written there, and then you don't need to type anything else, and just hit return, and it will say pair edit mode disabled in the current buffer. So I'm giving myself a new cursor. I'm going to enter a left parenthesis, and now we see that it does not try to match the parentheses. It's even more important up here in this source code buffer that we do that. So let's do that, Alt X, and then pair edit dash mode, and we have disabled it now in both the upper and the lower buffers. These buffers can be displayed, split up in different ways. If I come up here to the upper buffer and I hit Control X1, it will create a single buffer containing the information. If I type Control X2, it will split it again, but you notice this time now it has brought the source code down to the lower buffer. So let's talk about how we change buffers. You can see that this buffer is active because its name is highlighted. Now this one is active because its name is highlighted. We want to leave the source code here, but we want to get our REPL user cursor back down here. A couple of ways we can do it. One is we can put the cursor on the name. We can use the left button and right button. And it just so happens that when we press the right button from the source code buffer, that it did go to the REPL. But sometimes there's a lot of buffers, and it's kind of inconvenient to step through all of them. So what you can do is you can come up here under buffers, and you can find it up here. Here's our REPL buffer, and you can bring it back instantly. So two different ways you can change buffers. One more thing about the split screen, I'm going to type Control X1 and give us one screen. If I type Control X3 from the single screen, it gives us two screens. Now this looks a little crowded, but if you expand it out to your entire terminal, this is a nice way to work. What you can do is you can pull up your source code on one side, like for instance your definitions here, and then your source code on the other side. You can be working with some of these definitions later, farther down in the code, so that you don't have to be scrolling up and down. That's a very nice working feature. So Control X1, I'm back to the single buffer. Okay, so now let's talk a little bit about how this code works. The first thing that let's do is talk about the algorithm that we're going to implement here. As I said earlier, it's very simple algorithm, and it is based on three simple rules. First of all, let's take a look at the matrix here. Basically, all this is a long list of 400 elements, either dashes or X's. So the dashes represent areas where the bug can go, and the X's represent places where the bug cannot go. In other words, like a wall. The areas outside the matrix are also considered to be out of bounds. They're equivalent to an X outside the overall boundary of the matrix. But this is just one long list of 400 elements organized to make it look like a matrix. Now let's talk about the algorithm that we're using here. It's a very simple algorithm, and that is, if you ever get lost in a maze, all you have to do is stick out one hand or the other and touch a wall and keep your hand on a wall the whole time that you're walking forward, and you will finally manage to find your way out of the maze. So in this case, we are going to use the right hand rule. We're going to check to our right. So if the bug starts off here at the upper left hand corner and starts to traverse through the maze, it's going to find that there's something to the right here. It's following this wall. So the first rule is, if the space to your right is available or open, then turn to the right and move forward. So as it starts off here at the top left and is moving down this wall, it cannot turn right, but it's looking for its first opportunity to turn right. And here you can see that this space is open. Direction is important because when you're referencing forward or right or left or whatever, you have to know what direction you're pointed. So here it pointed to the right, and to its reference right, this is open, so it turns downward to the downward position and it moves forward. The second rule is that if you have something available open in front of you, you move forward. So the first rule is try to turn right. If you can't turn right, move forward. And then if you cannot move forward, for instance, if you're caught inside of a blind canyon like right here, if there's something to your right, you can't turn right. If there's something forward that you can't turn forward, then the rule is turn left. In other words, the opposite direction of the wall that you're following. And if you really think about it, it maintains the wall now on the right side. So it has turned to the right here. And then as it goes through the loop again, it says, well, can it turn to the right? No, it can't. Can it move ahead? No, it can't. So it follows the third rule again, which is to turn left. So now it's oriented to come back up out of this blind canyon. When it gets up here, it's going to turn right. It's going to come over here and turn right. It's going to turn right here. It can't turn right. It can't go straight, so it's going to turn left. It's going to come down here. So it will follow its way all the way through the maze in this manner, and it will appear as if it's doing a backtracking algorithm, but really all it's doing is following a wall. So if you look at one of these blind alleys, like for instance, if it comes down here, it's following this wall right here. When it comes down here, it's following this wall right here. So it comes down and then it comes back out. So it looks a lot more sophisticated than it really is. One question you might ask yourself, well, what if we had the left-hand rule? What if we were traveling, starting again here at 0, 0, traveling in this direction, but instead of keeping the wall to the right, we wanted to keep one to the left? Well, remember that this is out of bounds, so what's going to happen is it's going to continue down, trying to turn left. It's going to come all the way down here to the end without any opportunities to turn left. It's going to run into the end here, so it cannot turn left and it can't go straight. So the reverse situation of the right-hand rule is that instead of turning left, it would turn right. So now it's aimed downwards. So now it could come down this path right here. Or if it was a blind alley, it could turn all the way around and come back out this way, and then it could make a left-hand turn right here. And so anyway, it's going to work either way, whether you have a left-hand rule or a right-hand rule. Well, now that you understand how the algorithm works, the code is going to be fairly simple, and I don't see any reason why I need to go through it blow by blow. All you need to do is cut and paste from the description below into your buffer, the upper buffer, and then run it. If you have any questions or you don't understand how something works or why I did something a certain way, please leave a question below and I'll see if I can get back to you in a timely manner. So if I create our 2 buffers again and I put the lower buffer into the REPL mode, which will be when you open your Portacle, so you will paste the code into this section up here, which will be Scratch at that time, and then you can Control C, Control K, and you can compile it all. Come straight down here to your user cursor and type run maze 1, and it should run for you. So I hope that you got something out of this. Again, if you have any questions, I will try to answer them, and I appreciate your time. Enjoy. Bye-bye.